This is going to be our first video in a series on different integration applications. So for this first application, we're going to take a look at computing arc length. As the title implies, we're going to be working on using an integral to find the exact value of arc length. So let's go ahead and derive where that integral is going to come from. So our goal for finding arc length would be to take some sort of arbitrary function such as f of x, shown here in blue, and find the arc length. So when we think about length, we think about linear distances. We're commonly finding the distance between 2 points, and when you're trying to find the length of a curve like this, if there's no way to actually straighten out the curve and measure it, it becomes quite difficult. So we're going to start with an idea of approximating the length, and then using the same sort of strategies we've used with finding volumes of revolution, we'll turn that approximate into an exact arc length. So if someone was going to do their best to approximate this blue curve using methods that we know are quite easy for finding length, one thing that we could do is we could take our curve and we could partition the distance of the curve. So from A to B, partitioning means we're breaking it up into an even distance intervals. So the distance between each x sub I and x sub I minus 1 is equal. This we're used to. Instead of looking at rectangles and area, in this case we're looking at linear distance. So we mark the points that are actually on our f of x curve here in black, and then we'll connect those with a red line segment like so. And now, using that line segment, you can see that in a couple of the intervals, like this interval and this interval, that line segment is going to be pretty close to that distance of the actual curve. In intervals like the first one, it's going to be somewhat far off, but it gives us a tool for actually approximating. So we'll go ahead and write down the length. Let's just find the length of the ith interval. Okay, so when we find the linear distance, I want you guys to remember, think back to your geometry. We're just going to take a look at that first interval to get an idea of how we do this. If we look at the triangle that's formed by the line segment, what you might remember is that that's going to be the hypotenuse of a right triangle. So with a right triangle, what we can do is use the length of the legs to determine the length of the hypotenuse. So if I want to give like a quick little shortcut name to each side, let's go ahead and call this side delta x, and we'll call this side delta y. There's more precise and exact names to call it. Technically, if we were looking at a very formal proof in a book, what they would do is they'd call that xi minus x sub I minus 1. And this would be f of x sub I minus f of x sub I minus 1. And if it was negative, you'd have to take the absolute value because it's a length. So that will be what we let our delta x and delta y stand for shortcut purposes. So the length of the ith interval would be found if we went ahead and found the hypotenuse of that triangle. So remember, a squared plus b squared equals c squared. So in this case, delta x squared plus delta y squared equals hypotenuse squared. So if we want to find just the length of the hypotenuse, we would square root both sides, and that would give us that the length of the ith interval is going to be square root of delta x squared plus delta y squared. That's going to be the length of the ith interval. Giving you a second to just look at that. Okay, so now it's going to be kind of counterintuitive why we might do this, but thinking of the end goal being the fact that we want to be able to integrate something at the end, this particular style of writing the length of the ith interval isn't super friendly for integration. You might remember it's kind of hard to integrate square roots with too much going on inside. So kind of leaving it vague for why we would want to. We'll kind of see at the end why this might be motivated. So in any event, just doing some algebra here to change how this looks, I can go ahead and factor a delta x squared from my first term and my second term. Okay, we're working to try and get rid of this delta y squared. Remember, we always want to be working in terms of one variable. So that's why we're factoring that out. We're trying to see if we can maybe convert this term here to something else. Okay, so factoring out my delta x squared. Hopefully we agree that algebra is sound there. Now I can break this radical up into a square root of delta x squared times the square root of... We know that delta x is positive because it's always defined as a bigger x value minus a smaller. So this is delta x. And I can factor the fact that I'm squaring out. Now I have delta y over delta x quantity squared. So my full formula is delta x times the square root of quantity 1 plus delta y over delta x squared. Okay, the reason this might be beneficial at this point in time is because now I have I have a delta y over a delta x, which is the slope of a secant line. It's the slope of a line. We learned in Calculus 1 this really cool theorem called the mean value theorem, which means that if you have the slope of a secant line, it means that that slope has to happen as a derivative at some point. So if we kind of go back to our original picture, you see here's the secant line that we're looking at. Here's the delta y over delta x. The slope of this line is going to be equal to the derivative at some point. Like if I notice, look right here, that is a parallel. Let me get a better picture. Probably like right there, there's the tangent line that's going to be parallel. So instead of viewing this as some sort of slope that would be really hard to find in terms of delta y over delta x, we can say, well, by the mean value theorem, that's the derivative of some point in the interval. So this is by the MVT, by the mean value theorem. This is equal to f prime, the derivative of x sub I star, sum x Okay, so for some point in an interval x sub I minus 1 to x sub I, there will be some point for which that is equal to the derivative of the function. That's what the mean value theorem does. So now we're allowed to rewrite this as delta x times the square root of 1 plus f prime x sub I star quantity squared. And then we can go ahead and view this as a nice enough formula because I can see now everything's in terms of x sub i's. When I go to write my approximate arc length of the whole curve, remember we're going to range our I from 0 to n minus 1. And we have square root 1 plus f prime of x sub I star quantity squared times delta x, where n is the number of partition points, slices, whatever you want to call it. Okay, and then that gives us the approximate length of this curve. Now think about the picture. I'm going to zoom us out again, zoom back in over here. Thinking about the picture, how do we make this picture more accurate? You would want to make more and more intervals. The closer our slices, you can see the closer the slices, the closer you're going to approximate the length to the actual curve. So we're going to let our n, number of partition points, go to infinity. And as n goes to infinity, you guessed it, for the 100th time, delta x is going to go to 0. This f prime of xi star, the intervals are going to get shorter and shorter. So that xi star is going to end up just being a regular old x. So as n goes to infinity, delta x goes to 0, and we get the exact length given by the integral square root 1 plus f prime of x squared dx. And where do you start your partition? At A. Where do you end the partition? At B. Okay, so this is our exact length arc length formula. And again, when we look at these application examples, what's really important, anyone can memorize a formula, and the question is how long is it going to stay in the memory? But what's really beneficial is for you to understand where all these formulas come from. So if in a pinch, you can always understand, what you're doing, basically. For engineers especially, you're dealing a lot in the physical world and not so much in the mathematical world. So I think the meaning behind this is actually more important than the formula itself, if that makes sense. Okay, so let's go ahead and take a look at working with that formula. So let's say we were going to find the arc length of the curve f of x equals x to the power of 3 over 2 between x equals 0 and x equals 8. Okay, so the arc length of the curve, there's not a lot to draw here, not a lot of geometric reasoning. In these cases, I would suggest you can go ahead and just use the integral. So we're finding the arc length from 0 to 8. Okay, and our formula, square root 1 plus f prime of x squared dx. So now we need to find f prime of x. So the derivative would be 3 halves, x reduce the power by 1, so it would be x to the 1 half. So f prime of x squared would then be 9 over 4 x. And okay, now I'm hoping sincerely against hope this formula can produce a lot of hard to compute integrals. I'm hoping that this one's not so bad. It looks like it isn't. If I notice the interior of my integral is 1 plus 9 over 4x, looks like I could do a u sub here to handle that. So if I go ahead and let my u be 1 plus 9 over 4x, my du would be 9 over 4 dx. And I can correct, I don't have my 9 over 4ths, I want it, so I'll go ahead and add it in. So multiply by 9/4, and then on the outside, multiply by the reciprocal to cancel that correction factor out. So we've got 4/9 integral, and if we're going to change our u, our interior variable, we need to change our limits of integration. So plugging in my endpoints, I get 1 plus 9/4 0 gives me 1 for the lower limit, and for the upper limit I get 1 plus 9/4 times 8, so I get 9 times 2, so 19 I believe. Yeah, 8 4 2 19, and then square root of u du. So this is equal to 4/9 times, that's u to the half. So using the power rule, we up the power by 1, we get u to the 3 halves, multiplying by a 2/3 out front, and evaluating from 19 to 1. I'm going to go ahead and handle this. We got 8 over 72, we'll pull that out, and 19 to the 3 halves minus 1 to the 3 halves is just 1. Okay, can I easily compute what that is arithmetically? No. A calculator would need to approximate what 19 to the 3 halves is. So I would say just go ahead and leave your answer like that to be exact. Now, if you use a calculator, is it going to give you that? No, probably not. It's going to numerically approximate the integral, and it'll give you like a decimal, which, sometimes it's good, and sometimes we do want to find the exact. So we very much practice both in this course. Okay. So the arc length is a fairly simple formula. The most challenging part of it generally is just the integration step, and this example is going to motivate why in the future we're going to want to have more integration techniques under our belt in order to handle these kind of complicated integrals. In the event that we couldn't integrate something exactly because the function's non-integrable when you plug it in, that is why we revert to our approximand. So remember, how would we do this? We would compute our Riemann sum to approximate the arc length. This is the end of this arc length video, and in the next video we're going to cover the integration application covering density. See you then.